Our next speaker is Matt Bridle, who's a certified training instructor with Doulos. He's going to talk about class-based design verification with Python Cocotb. Matt has been writing and delivering training courses for Doulos since 2007, specializing in digital design and verification, VHDL, System Verilog, Python, and C++ programming for embedded systems. Since graduating from the University of Cambridge with a BA Honours in Computer Science, Matt has been in the electronics industry for more than 25 years. In the engineering and support teams at ARM Limited, he worked in the development of VHDL, Verilog, and C-based hardware modeling technologies, as well as in training and support for their customer base. Matt also worked for a number of years on implementation of FPGA signal processing designs in VHDL.
Great, thanks, Mike. Hello. So before I get going, I just have to remark on how wonderful I think this lecture theatre is. It's got great wood panelling and inset lights and everything's lovely. There's a couple of screens down here so that I can see what you can see on there too. It's very clever. Thank you for coming. I'm going to be talking about Cocotb, and I'll just give you first a little rundown on what Cocotb is. So stands for coroutine based co-simulation test bench environment, created by Philippe Wagner and others. And the idea is that it's based on Python and it uses Python to do hardware verification. And obviously there's some stuff that needs to be added to Python to make that work. So Cocotb extends the reading and writing, enables reading and writing of HDL design elements so that you can actually look at what's going on your ports and probe into your design and see what's happening and so on. And also, if you want to drop values in either on the ports or in the body of your design. It also handles the concurrency and synchronization. Some of this is actually native Python anyway, because Python does have a certain level of support for concurrency, but Cocotb then builds on that because the requirements of hardware verification are quite significant in terms of how concurrency works. And it just generally makes it easier to write verification components. There's some verification IP available, and there are some kind of more standard ways of working that just make life more easy rather than having to work in a totally software mindset. It's open source, yay, which means that you can use it on pretty much any simulator. Support for the level of support varies a little bit between different tools, but it works with a very large number of commercial and free simulators. And if you want the official version, as it were, go to www.cocotb.org for more details. So this is just a diagram of kind of Cocotb's way of working. So we have we have the device under test in the middle, and then we have that running in a simulator. So we do need an HDL simulator that does all the normal stuff that it does. So your actual design sits in an HDL simulator, VHDL system, Verilog, whatever. And then the Python interpreter runs the Cocotb side. So you run a Python program with the Cocotb package, and that runs in the Python environment, and then that's communicating to the HDL simulator by means of an API. And which API it is depends on what kind of simulator. It's typically VPI or VHPI, depending on whether we're in System Verilog land or VHDL land. Why are we bothering with Cocotb? Well, part of the reason is that a lot of people already know a lot of Python. So people coming out of university now, that might be some of you, I can't see how old you all are from here, but you probably learned Python. I didn't. I learned Modular 3 and stuff, but you probably learned Python as a first programming language. And there are an awful lot of people now who know Python or are familiar enough with it for it not to be learning a new language to do a new job. And also, if you're kind of familiar with that and you're kind of new into maybe FPGA design, just to make things, you come up with an idea, you want to make it run faster, the software isn't good enough anymore, you don't really want to have to learn a great big new language or verification methodology to make it all work. You could, go the whole way, learn System Verilog, learn UVM and all that malarkey, but you might not really want to do that. Maybe you're going to use this again in the future, maybe you're not. So actually using something that's familiar is an advantage. It has support for many industry standard simulators, as I said. So we're in a situation where it's very very accessible to a lot of people with a lot of different tools. And Python, of course, has a huge base in terms of the number of packages available, and that's really useful for doing things like generating reference data. And so you can actually have alongside your HDL description, you can then have a reference model, which is generating in Python all the data that you want. And a lot of that stuff is already out there for you for signal processing applications, networking applications, and so on. So here's a simple Cocotb test. As you can see, it looks like Python code because it is Python code. So a couple of things to note. So here we're just, oops, that's the wrong button. So here we're marking a test. So we have a decorator to say what you're actually going to test, and you can have a number of those tests that you run. And every time it sees that decorator, it says, okay, that's a new test I need to run. We also have the ability to write values into our inputs of our design, very straightforward. Wait for a certain amount, so you have this concept of triggers in Cocotb, and the timer is one of those which allows you to wait for a certain amount of time in your simulator. And then we can use standard Python assertions to check that the outputs are actually what we're looking for. And if we fail that assertion, then the Cocotb test will fail and report a failure. So it's nicely integrated into the Python assertion mechanism like that. And running a Cocotb test is also pretty straightforward. You can have a makefile-based flow, and there's a PyTest-based flow, or you can run Python native, or you can actually integrate the whole thing into your own design flow, a verification flow, rather than having to necessarily learn how to do that too. And it uses the standard Python logging module for formatted output. So not just plain messages, but the kind of standard simulator stuff that you get with the time and the severity, and this is where it came from, and that's your message. So that's really useful. The Python pretty much already has that, and Cocotb makes the most of it. And at the end, you get a nice little box saying what passed, what failed, and everything. And if it failed, then you have some more details as to what actually broke on the way, and you can then you get a trace back, and you can see what caused the issue and go and fix it, or go and tell your colleague to fix it because they're the designer and you're the verification engineer. So, great, we've got Cocotb. But how do you actually structure your verification framework? Well, this is the kind of old-fashioned way of doing it, and this is perfectly decent if all you're trying to do is simple block-level testing. Nothing wrong with this for a kind of fairly small self-contained block. You have your device in blue, and you have your test bench in that lovely mustard colour. My wall at home has painted that colour, by the way. I really like it. But this doesn't scale very well. The trouble is that although it works well for something that's kind of small and which you can, and maybe for glass box testing where the innards of it anyway, and that's how you're kind of constructing your verification. For a large system or a subsystem, this does not scale well. And we end up having to change everything every time we want to do a new test or test a new feature. So verification engineers have been working on this for a very long time, and they've come up very sensibly with a model which is more reusable and more configurable, something a bit like this. So this is not one particular example. This is just kind of something that I and others at DDoS have put together. So it's not a known framework, but these are the kind of components that you will find in a verification framework. So, for example, we've got this bit in the light blue here is the test harness. So this is everything which really needs to know what's happening on the pins. So everything outside of that block can then be written in a much higher level manner, and it can typically be based on transactions. So the idea of saying, please can I do a read from this address, please can I do a write to that address, that sort of thing, rather than, okay, let me assert the write enable and then wait for a cycle and then assert the address and blah, 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 all that stuff. So you can actually think much more easily about the tests that you're trying to write and construct them more straightforwardly in the rest of the framework. So everything which has to be changed when you run a new test can just work at that transaction level. So we've got here a stimulus generator, which will be generating stimulus in terms of, say, read and write transactions. We've got transaction recording, so we can look at what's happening on the device as transactions and log that. And the conversion between the transaction world and the pin level world is done by means of bus functional models, or BFMs. I always think that ought to stand for Blue Fairy Monster, but it doesn't. So these are BFMs, a driver and a monitor. The driver is responsible for taking the transactions here and converting them to pin level changes. And The monitor is responsible for watching the pin level changes and converting them to transactions for the rest of the system to consume. And you can see we've got other things on here too. We've got a coverage collector, because we may well want to do constrained random stimulus generation and coverage, yum yum, which is a much easier way of answering the question, are we done yet, as well as did the test I just ran work? So I'm not going to talk in lots of detail about that, but I will go into how we can do it in Cocotb. So we need a tidy way to implement verification components. We need a tidy way to implement transactions, and ideally with randomization, so that we can do some kind of stimulus generation based on random data rather than having to do directed tests, which are laborious to write. And we want communication channels, because these components need to be able to talk to each other in a sensible way. We also need concurrency and synchronization, partly because hardware is just naturally parallel. When you switch the chip on, everything comes to life at once. It's not like software. And software engineers moving into hardware often have this mindset they have to just shift. Oh, goodness me, everything comes on at once. And we have to think like that, because although Python is a software language, actually, when we're simulating hardware, we have to think about actually, although there's data flow from one end to the other, actually everything's always happening. And also, the verification environment itself needs to have a level of concurrency, because each component will need its own thread. So they'll need to be autonomous, otherwise it's not very reusable. We want to have a situation where all of our components will do their job as necessary without really having to think about what's around them. They just take what comes into them and send it out to the next chap, and everybody's happy at that point. So they need their own threads, and they need a good way of communicating between. And also, some verification IP for well-used bus protocols would be a bonus. So I'm now going to talk a little bit about a proposed reusable Cocotb verification solution. So how does it solve concurrency? Well, concurrency in Cocotb is managed using Python coroutines, which are built-in asynchronous functions. I don't mean the functions are built in, I mean the mechanism is built into Python. And then it also uses triggers and events, which are additional classes that Cocotb adds to Python in order to enable synchronization between different threads. And there's a queue for message passing. So that's basically a FIFO, and it enables us to read at one end and write in at one end and read out at the other. So here's a bit of Cocotb code. We've got, this is a coroutine, so we've noted the word async, meaning it's an asynchronous function. And what we're doing here is very simply taking our device, which is supplied to your Cocotb framework by the infrastructure as a handle to your device. And then we're simply setting a couple of values and waiting for 5 nanoseconds. This test here then can actually call this thing as a coroutine. This wait needs to be awaited for rather than called in Python because it's a coroutine. You can see it's pretty straightforward. They don't have to write much more than ordinary Python to do this. I'm not going to go into masses of detail about all this code, just point out a few things as we go along. So the transaction can be implemented as a Python class, which you might expect from having done the same thing in System Verilog wherever. And we can actually generate random data using Python. So we can create a randomization routine, for example, randomization method for our transaction class, which actually calls Python a random package to generate random data. And there is a certain level of constraint we can add. We can add weights and things to choices that we make and such like. We can also implement our verification components as being classes too. So here's an example of a monitor class. So that's watching what's happening on the pins of our device and translating those to transactions, which is then going to be kicked out to something like a checker or logger or something of that kind. So we've got waiting for a rising edge, nice and easy. Again, Cocotb allows us to do that very straightforwardly. We're creating a transaction object here, having observed what's happening on the pins of our APB in this example. And here we're using a Cocotb queue. We put that transaction into a queue, and something else will consume that. There's also some IP available. So Cocotb bus is another package associated with Cocotb that contains base classes for a lot of verification components and some for specific bus protocols as well. So this driver, for example, actually uses the driver component for Cocotb. So it extends the driver class, and this driver send is then what's implemented to actually create the pin changes from a transaction that it was passed. And we can also then do a get from the queue that generated the stimulus transactions. Again, that's the Cocotb queue class being used there. And we can do both non-blocking and blocking gets as we need to. And happily, we can also do the synchronization of everything together. So when I was putting this example together, it took a bit of work to work out exactly how I should start each coroutine. Cocotb actually provides several different ways of starting coroutines. There's the await, which literally waits till it's finished. There's a start like this, which is starts it in its own thread and then returns. There's also a start soon, which allows you to start it the next time the parent thread suspends. What we're doing here then is setting each of these different verification components of running as a separate thread. And then at the end, we have an await for this thing here. And this finish is an example of a Cocotb event object. And that allows us to synchronize between different places. We can basically signal that event when we finish. So this is being passed into the checker, for example, and the checker will be the checker can then be told when everything is over. It's the other way around, actually, isn't it? The checker tells everything when it's over, and then that will then say, okay, I'm done now, and we've finished the test. So this, again, that extra level of synchronization and concurrency is built in to Cocotb itself. So for random stimulus and coverage, if you want to go further, there are some other Python packages that you can actually look, which are being developed to do exactly this, to exactly solve this problem for constrained random stimulus generation in Python natively. So that's constrained random and PyVSC. So happily, we've answered our questions. For verification components, we have Python classes. For transactions, we have Python classes. For randomization, we can use Python random and other packages if we want to. For communication, we can use Cocotb queues. For concurrency and synchronization, we can use coroutines to manage the fact that we have our parallelism, and we can also have different verification components running in different threads. And there is some verification IP available in Cocotb bus. So in conclusion, we can have our cake and eat it. We can have the advantages of Python and Cocotb, and we don't need to compromise the robustness of the methodology. We can do it properly. So I hope that's been helpful. We're developing at Doulos a Cocotb course right now. I'm in the middle of writing it. So if that's something you're interested in, do come and have a chat with us later. There's a whole bunch of other courses and topics that are available as well, with design verification, embedded Python, and so on.
Okay. Only quick questions from the audience. We literally have 1 minute. Oh, thank you. Sorry, Matt. I always forget to say thank you and give it a little clap. But yeah. Yeah, Surinder, I'll be there because lunch is in 1 minute. So remember, people want to get in the queue. So don't make it short.
Many years back, there was a facility or a feature called Specman, which was an aspect-oriented language. It had all the features which today's Cocotb or Python supports. I would like to understand, are not we re-engineering everything, meaning redefining everything?
Yes and no. So we can reuse all of the same techniques and thoughts and ideas that came from that, and actually a lot of that's made it into System Verilog anyway. But the point is, we don't have to learn Specman, System Verilog, or whatever. So Cocotb is the main two advantages in Cocotb are the fact that a lot of people know Python already, and also the fact that there's a lot of Python packages out there for the data generation side of it, which is not quite the same for somebody learning Specman or System Verilog or whatever.
And pricing. The third one, which is very important to people. Okay, that takes us straight into lunch. So thank you very much. I hope you've enjoyed the morning. I can see lots of movement between streams, which is healthy, I think. And we will be starting, as you know, we're pretty strict with the timing. It's 1:30. So you've got an hour for lunch. Enjoy. And don't forget to go to the stands and talk to our sponsors. We need them to come back next year and pay for you to attend again. And don't forget your voting forms. We need feedback on the speakers, please.